Hi, my friends. We are going to do part one of repeated eigenvalues today, which is really just the first case that we see. We have two different cases, and so once we kind of get into this, you'll have a better idea of what those look like. So basically, with case number one, what happens is the multiplicity of the eigenvalue, meaning when we have repeated, right? So if it's repeated, we would say like the multiplicity is 2 or maybe 3 if you get that many repeated. We would say that that multiplicity is equal to the number of linearly independent eigenvectors that we can find. So we've talked a little bit in the past couple of sections about how important it is for our eigenvectors to be linearly independent, meaning that they're not scalar multiples of one another. So we're going to do an example here of a 3x3 to just get into what case number one here looks like. And then you could probably guess, now that we've just said this, that case number two is going to look like when the multiplicity is not equal to that same number of linearly independent. What happens when they are, in fact, scalar multiples and we don't have distinct eigenvectors that we could find. So we're not worried about that today. Today, we're just going to look at what happens here. So you've probably seen, and I have not been good about calling this in the videos, but when we do our determinant here, we get a characteristic equation. So once we find the determinant of A minus the lambda identity matrix, set it equal to 0, that this is what we call the characteristic equation. And like I said, I have not been very good about referring to it in that way. So here's kind of a good little, it's the characteristic equation. There you go. Instead of us doing that together, I hope that you've been practicing and you're okay with doing the determinant of a 3x3 on your own here. So I'm just going to give you the characteristic equation. It is lambda plus 1 squared times lambda minus 8 equals 0. So what we get is we get a good lambda sub 1 here of 8. That's good. But then we do get a repeated eigenvalue with a multiplicity of 2. So we're going to go ahead and evaluate that here in a second. Now, I'm going to skip the part where I go through and plug 8 in and work out the eigenvector, just to save us a little bit of time on this video. Again, I hope you're practicing all of those things. So let's just say that when we use a lambda sub 1 of 8, that this would be what the matrix would look like. Okay, and then our job here is to find all x sub 1, x sub 2, x sub 3 in that eigenvector. And again, you do any kind of row operations you want to do if you want to try and, go through and practice that. It would not hurt. I will just tell you, though, what I got for that corresponding eigenvector is 2, 1, 2. Okay, so we'll move on. Let's go ahead and look at the case where we have our repeated. So when lambda sub 2 is equal to -1. All right, again, I'm going to go ahead and give you the matrix here. All right, and I'm going to go ahead and just augment that with 0. This is what we would do to do our row operations and simplify. But as you can see here, if you kind of notice when you're going to fill these out, every single row here is a scalar multiple of row 1, essentially. So basically what that means is that I could take 1/4 of row 1, and I'm getting 1, 1/2, 1, and everything else would simplify down to that. I mean, again, I could do 1/2 of row 2. I could also take 1/4 of row 3. Every single one of them would come out to be the same thing. So essentially, once I do my row operations, and I mean, I could write them off to the side here, but what's going to happen is every single thing is going to eliminate from those bottom equations, meaning that I don't know if you could tell that that notification scared me. But this means I don't get a whole lot of help from my other two equations. I just have to go off of what I have for my top equation, which says that if I have x1 plus 1/2 of x2 plus x3, that's equal to 0. Now, what happens is I can actually figure out a couple of eigenvectors here. So I'm looking for x sub 2. I could say that, x1 and x3 are equal to 1 and, or I'm sorry, 1 and -1, and x sub 2 is 0, just to make my life easier, get rid of the fraction there. So I make x sub 1, 1, and I make x sub 3, -1. Okay. Now, obviously, I can't just flip those because that wouldn't be linearly independent. But what I could do for my eigenvector x sub 3 is I'm going to try and eliminate my fraction here, just multiplying it by a 2. And so what I could do is keep x sub 1 as -1. And if I just make this a -2 and then just, eliminate x sub 3 by making it 0, that's a linearly independent eigenvector. So that's great. They're all linearly independent, including the one that we have up here for x sub 1. So this is awesome. That means that, we have a fundamental set and all is good in the world. So actually, I think I have it down here. Yep. All right. So for this case, the algebraic multiplicity of our repeated eigenvalue is equal to the geometric multiplicity, meaning the number of linearly independent eigenvectors that correspond. So just to, give you some clarification, the algebraic multiplicity means of my eigenvalue that we got there for lambda sub 2, the multiplicity here was 2. Okay. Now, my geometric multiplicity, I was able to find an x sub 2 and an x sub 3 that were not linearly dependent. They were linearly independent. And so the geometric multiplicity here was 2 because they were two distinct eigenvectors. So if that's the case, then life is kind of good. And what we do for our general solution is we go ahead and say that y of t is equal to, for our example, c sub 1 e to the 8t. This is for my first eigenpair that I found right here, plus c sub 2 e to the -t. And for that first eigenvector that we found, 1, 0, -1, and then just go ahead and do c sub 3 e to the -t there with the second eigenvector. And, for this one, we don't really have to do a whole lot of extra work because, I don't have to worry about that e to the -t getting multiplied by an extra factor of t. Just as a little heads up that we do deal with case 2 similar to how we deal with repeated values, repeated roots when we were solving before. So this is really it for this video. Just give you a heads up, this is not the most likely scenario we'll come across. That will be case 2, which we will talk about a little bit more tomorrow. So I hope you're having a great day. Good luck on the practice for today, and let me know if you have any questions.